Today's lecture concerns two of the transformation factors that allow us to convert money in one form of payment to money in a different form of payment. The two we're looking at today are the capital recovery factor and the series present worth factor. You'll recognize this diagram. It shows the transformation factors between the different kinds of payments. Present worth, which is money today, future worth, which is money at some point in the future, an annuity, which is an equally spaced series of payments, and a gradient, which is a series of payments that increase in time. Today we'll be looking in particular at the relationship between the present worth and an annuity, and examining the capital recovery factor and the series present worth factor. The capital recovery factor allows us to convert a present worth to an annuity, whereas the series present worth factor allows us to convert an annuity to a present worth. Before I move on to the transformation factors in detail, I'd like to remind you of how an annuity works. I have in this diagram an annuity of 6 periods in length in red. We discussed in the previous lecture a future worth, here for n equals 9. Today we'll be looking at a present worth, which would be at time equals 0. And again, it's a single payment. And you wouldn't normally have a number of periods involved because it's not in the future and it's not a series of payments. And the symbol we use for present worth is P. The first of the conversion factors we're looking at today is the capital recovery factor, which converts a present worth into an annuity, or finds an equivalent annuity to a given present worth, for a particular interest rate I and a number of periods capital N. And to introduce the formula, I'd like to do that through a problem. Here's a typical engineering problem, if you like. We're given the information that it will cost $10,000 to overhaul an old packaging machine. The work is expected to improve production over the next 5 years. How much savings per year will be achieved for this investment to be worthwhile at 55% interest? Now, there's a couple of features of this problem I'd like to mention before we actually work on the capital recovery factor. First of all, this is different from many of the problems we've seen before in that the interest we're gaining is not due to a clear investment like the bank or something else where money is received directly. Here the interest is received as improved production. We're getting savings from overhauling this packaging machine, and these savings are represented as dollars and are quite legitimately considered to be interest. The other feature of this is this 55% interest. Now that seems way out of line for what we'd normally expect interest rates to be. We expect interest rates to be anywhere from 2 to 15%, in that range, depending on the economy and so forth. But this 55% interest seems way out of line. Well, as we'll see in subsequent lectures and material in this course, that depending on the circumstances, this may be a very, very reasonable interest rate. Because interest has much more meaning than the kind of investments available to consumers. Interest in this case is the kind of return one can get within one's plant by appropriately investing one's resources. And if it's a very dynamic operation and the company's making lots of profit and capital is scarce, this 55% interest may be quite meaningful. We'll see more about that later, but I wanted to introduce this now to give you a feeling for what might in fact come in the future. Now, as far as the capital recovery factor goes, if we're trying to figure out how much savings that we'll need to justify a $10,000 expense, we can look at this in a trial and error way. For example, we may take an amount of money sort of arbitrarily and assume that we're going to get savings of that. Let's take $5,000. Just arbitrarily assume that we're going to have savings of $5,000. Well, if at the end of the first year we've saved $5,000 on this overhaul, we can calculate, using our present worth factor, what the present worth of that future savings would be, yeah? As $5,000 times 1 over 1 plus 0.55 raised to the power 1. That's our present worth factor, which we learned in the previous lecture. And because that interest rate's so high, that actually reduces the present worth to $3,225.81. So what we're saying here is that if we're saving $5,000 per year with this overhauled packaging machine, the present worth of that $5,000 at the end of the first year is only $3,225. Similarly, if we make the same savings in the second year, we'd have $5,000 now brought back in time 2 years. So it's 1 over 1 plus 0.55 raised to the power 2, which is $2,081.17. So the benefit today of the savings in the second year are diminished. And we can do that over the 5-year savings that we're told could be achieved with its overhaul. And we'd have the $5,000 times 1 over 1 plus 0.55. 3 years from now, four years from now, and 5 years from now. And the amounts that these future savings would be equivalent to in today's dollars would be diminished the further in time in the future you go. So we've got $1,342 for the savings in 3 years, $866.25, and $558.87. Now, for this guess of $5,000 savings then, if we total the present worths of the individual savings per year, that would give us the present worth, the equivalent dollars today to all those future savings. So if I total that, that's $8,074.79. So this is saying that even if this overhaul saves us $5,000 per year, it really isn't justified by our $10,000 expense today. Because those $5,000 savings each of the 5 years are only equivalent, when they're totaled, to just over $8,000. So we have to save more than $5,000. And we could go on with a trial and error process like this, choosing a value that we think might be saved, and working out a present worth for all these future savings, and seeing how close it is to $10,000 until we narrow in on the one that gives us a $10,000 savings. But that's kind of hard to do. And of course, there's an easy way of doing it. By doing the same process I just did, using common sense with the $5,000 savings, on some symbolic saved amount, which of course will be the symbol A, because this is an annuity. So if my savings is A at the end of each year, I can work out the present worth as being A times 1 plus I to the minus 1 for the first year, and A times 1 plus I to the minus 2 for the second year, right down to A times 1 plus I to the n minus 1, and A times 1 plus I to the n in the nth year. And if I sum up all those present worths, I get a relationship between the present worth of the annuity and the annuity itself. And that's then 1 plus I to the minus 1 plus 1 plus I to the minus 2 plus dot, 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 1 plus I to the capital N minus 1 plus 1 plus I to the n. Now, you saw in a previous lecture some mathematical manipulations that allow us to simplify this expression. And we can do that again, and if you wish, you can try that as an exercise at home. But what we end up with is A equals P times I times 1 plus I to the n over 1 plus I to the n minus 1. So that the capital recovery factor, A/P, I% capital N, is equal to this part, the I times 1 plus I to the capital N over 1 plus I to the capital N minus 1. And just because I forgot to mention it earlier, this name, capital recovery factor, you can see comes from the very kind of problem we're illustrating here, where we're investing capital, the $10,000 into overhauling the packaging machine, and we're recovering it with savings. So this tells us, the A, how much savings we have to recover that capital investment. So for our original problem, we've got a P of $10,000. We've got an I of 0.55, and we've got an N of 5. So from our capital recovery factor, we've got A is equal to P times 0.55 times 1 plus 0.55 raised to the 5th power over 1 plus 0.55 raised to the 5th power minus 1. And if we calculate that out, that gives us the answer of $6,192.12. Now, another point about this answer is that our intuition would suggest that if you're spending $10,000 to overhaul a machine and you're going to be saving $6,000 a year on it, and you'll be saving that for 6 years, your intuition would say, well, that's a good investment. But in fact, if you only save $6,000, it's not. And it's because that interest rate is so high. If you're only saving $6,000 because it's less than this amount, it would be a good investment. So that's the capital recovery factor. Its reciprocal is the series present worth factor. The name series present worth factor makes sense because you're finding a present worth from an annuity. An annuity is a series. And it's simply reciprocal, so that it's just going to be the 1 plus I to the n minus 1 over the I times 1 plus I to the n. Here's a word problem. How much should be paid for a tube bending machine, which will save a total of $25,000 per year over its 10-year life with interest at 25%? So in this case, we know what the savings are, and we want to know how much we should pay for the machine. So we're looking for a present worth. We're given an annuity of $25,000, interest of 25%. Number of periods is 10. So the present worth from the series present worth factor is going to be the 25,000 times 1.25 to the 5th minus 1 over 0.25 times 1.25 to the 5th. And again, if we work that through, that gives us $89,262.58. So in this case, if the savings are $25,000, we wouldn't want to pay more than $89,000 odd dollars. If the tube bending machine costs $90,000 or $95,000, that would be too much. It wouldn't be justified by the savings. So that's the series present worth factor and the capital recovery factor. Allow us to find equivalence in payments between present worth, money today, and annuities. And these can be very, very useful in engineering calculations. We'll see more of this in the future. Thank you.